we have the line assumption. For simple linear regression and for multiple linear regression, we have the line assumption. What does that stand for? What is line? What is line? L basically means there's a linear relationship between the mean response at x. There's no, you cannot say there's a linear relationship between y and x, but there's a linear relationship between the mean response. And basically between the e of y and x. There's a linear relationship. What is I? I basically means the arrows or the epsilons here are independent of each other. Because the epsilon are independent of each other, all the y's are also independent of each other. The first part of y is a constant once you give a x. And then the later part, you add a noise, Gaussian noise. If this is independent, y is independent, okay? So epsilon being independent means, epsilon I being independent means yi being independent.
Professor.
They also need to add I, e yi have a linear relationship with xi. Yes?
Someone said that you're not recording.
Oh, sorry. Ooh, terrible mistake. Yeah, I would normally forget, but today I added just talk about the homework. I thought it's like a, oh, all right. So because the epsilon I are independent of each other, that makes yi also independent of each other. That's the I assumption. What is n? N basically means all the epsilon's i's are normally distributed. Right, they are normally distributed. Because of that, that also makes y normally distributed. Why? Because the first part is a constant plus epsilon I. If this is normal, a normal random variable shifted by a constant, it's just like located at a different location. It was here, shifted to here, it's still normal. And also there's a E, line has an E. E means equal variance. All the epsilon I have equal variance. Because they are equal, we just use sigma square. If they're not equal, you would have to use the sigma I square. For each I, it has different variance, but right now it has equal variance. We don't have sub I, we just call them all common variance sigma square. Okay, in the derivation we talked about earlier, we have been using this because every time we say what is the variance of y, we just say sigma square. We don't have sub I here. That's because there's assumption for equal variance. So these are assumptions we have used in the multiple linear regression and the simple linear regression. But what if something is wrong? So today we talk about some intuitively, it just visually you can inspect. That will be later half of the class, okay? So the first part we will check the residue. This comes from section 3. Section 3, some measures about the residues. So residues here, let's say EI equal to YI minus YI hat. EI is different from epsilon I. Epsilon I is the Gaussian noise added to the linear component. That gives you the observation YI, but the EI is what you observed minus what you have predicted by your regression line. Okay, EI is not the same as epsilon I. All right, so what kind of distribution does EI have? What kind of distribution does EI have?
Should be normal, I think.
Yes. Why?
Yeah, since y is normal, I think it should be normal as well.
Why is it normal? And you have to say y hat is all normal, right? But why is y hat normal? Y hat is beta 0 hat. Let's say just a simple linear regression. Beta 0 hat plus beta 1 hat xi. Xi in the linear regression, in the regression class is considered a given constant, okay? But beta 0 hat, beta 1 hat are normal, right? So it's linear combination of normal, so y hat normal. This is something we proved earlier. Don't forget the conclusion. So difference between two normal still normal. How about the mean? What is mean EI? What is E of EI? Zero, yes. But you need to be able to write it out. What is E of EI? That is E of yi minus E of yi hat, right? What is EYI? Let's say, because of the idea is same for multiple linear regression, I might just write out for simple linear regression with one variable. Beta 0 plus beta 1 xi. That's EYI minus, what is EY hat? EY hat will be E of beta 0 hat, E of beta 1 hat, xi. But the E of beta 0 hat, beta 1 hat, each one equal to the true parameter because they are unbiased. So you plug in E for each of beta 0 hat, beta 1 hat, you get beta 0. You get beta 1 xi. Okay? 0, right? So basically you have normal distribution with 0, mean. What is the variance? Variance probably takes more lines of derivation. Let's put it here. What is the variance of EI? If it's not easy to see, let's try to use a matrix form. Let's say E equal to, as a vector, y minus y hat, right? Column vector, column vector, column vector. This can be written as I minus H y. The y hat is hy. With this, we can write out what is variance of E. You will have I minus H, variance of Y, and I minus H transpose, right? And variance of Y, we already said if it has a common variance, each yi actually have the same variance sigma squared. So variance of y, also it has an independence requirement. So basically it is just sigma squared times a identity function, right? Identity matrix, I minus h, sigma squared times I, that's an identity matrix, and I minus h transpose. Then what? Because this is scalar, this is identity matrix, you basically have I minus h times I minus h. Remember, I minus h is also symmetric and idempotent. Idempotent means something multiplied by itself is still itself. So eventually you have sigma square I minus h. It becomes very easy, right? Why there is I minus ht? You are talking about this part. This is when you take consider this is constant. This is a random variable. The variance of a constant multiplied by a random variable is the square of the constants multiplied by the variance of that. Square in the matrix form is you put it one here, you put one here. To make sure the dimension matches, so you can do the multiplication. If it's a scalar, you would directly say, okay, the variance of a times x is a squared times variance of x if x is a random variable, a scalar form, but this is a vector. All right, now we have variance of E, and we also know all the EIs are independent. In that case, the covariance, the variance here is matrix. Okay, the off-diagonal position will have to be 0 because EIs are independent. So EI and EJ have 0 covariance. So you only just have a diagonal. Off diagonal is 0. So in this case, what is the variance of EI? It will be just the diagonal position from here, right? So it will be sigma square 1 minus HII. HII is diagonal position for H. So in this case, what is the purpose to get the distribution? We get the distribution in order to find the test for it, right? So we are able to fill in here. The distribution of EI here is normally distributed with 0 mean and sigma square 1 minus HII. Oh, I misspoke here. So for this one, we just take the variance. That's not to talk about the covariance yet. Okay, just take the variance from the diagonal position. We cannot say it's a off diagonal is 0 yet. Okay. So in this case, do they still have common variance for EI? We have common variance for epsilon I, but epsilon I and EI are two different things here. Okay, obviously every EI has different variance because you have HII. Different I will give you different value. All right. So in this case, for each of EI, if we know the true variance, what kind of test can we do? We know the distribution already.
And no more.
Z. So
Z,
if we
Z.
know the true, it will have a Z test. The test statistic will be Z. Let's define Z sub I because each EI already have different variance, so you don't have a common test statistic. You have a test statistic for each EI. So I define ZI equal to EI. You first d-mean it, then divided by the standard deviation, right? But mean is 0. Mean is 0. So you have EI divided by sigma square root of 1 minus HII. This one follows normal distribution with 0, 1. This is a Z distribution, right? Sometimes we call standard normal as Z distribution. So what's a good thing about knowing the distribution? Once you know the distribution, you can test what is the small probability, right? For all the hypothesis testing, basically, if the calculated test statistics actually is unlikely to happen, if it's unlikely to happen, it's very small probability. You can reject the null that assume all the model assumptions are satisfied. Because under the null means all the model assumptions here are satisfied. If it's a small probability, that means it's not. But at this point, we still don't know what assumption is violated. Okay. So this is when you already have a sigma known. What if it is not? What if the truth variance is unknown?
They'll use the t-test.
Right. You have the right start, but actually we cannot conclude it's a t-test yet. You can define something similar, but it's not a t. So if it's unknown here, you would define something, let's say Ri. This Ri has nothing to do with correlation. I just name the random variable as Ri. As similar to this, you'll have Ei divided by, replace this sigma by the estimated one, by the sigma hat. You still have square root of 1 minus Hii. Everything same, just replace the sigma by sigma hat. So what is your sigma hat? Your sigma hat squared, this is the estimated variance, SSE over n minus p minus 1. That's the formula. SSE divided by its own degree of freedom as estimate for the variance here. From here, you can get the sigma. So the Ri we define like this. Do you think it's T? This actually is not T, okay? Does not follow T distribution. One of the condition is not met. Remember, in the definition of T distribution, you need to have a Z random variable divided by square root of a chi-squared variable divided by its own degree of freedom. These two we satisfied. However, there's also a third requirement that the top and the bottom must be independent of each other. This is the part we don't satisfy. Ei and SSE are not independent, okay? The sigma hat is computed by sigma hat squared, right? This one use SSE. Ei and SE not independent. So we don't satisfy the independent requirement, we cannot say it's T. All right? So even though it doesn't satisfy T, but we still can, this is not basically, rigorously speaking, it's not a T distribution, but we still can come up with some like a roughly threshold, roughly like a cutoff value. Let's say if the absolute value of Ri here greater than 3, we just consider the data outlier. This is the ith data point. Consider xi, yi. Xi is given as constant, but your main point here is yi, a outlier. Okay. That's just a rule of thumb. Rule of thumb, okay? Not strictly speaking from the statistical sense. So people still can use this in practice. If your calculated Ri has absolute value greater than 3, consider this data point, the ith data point, ith observation, a outlier. So what is the rationale to come up with 3? How did you come up with 3? This 3 here come from the, in practice, people use the 3 sigma rule. Do you know the 3 sigma rule? For normal distribution, 99.7% of data lie within 3 sigma of the mean. So in practice, let's say you have standard normal. This is your mean. Some percentage of data within 1 sigma range. This percentage is about 6 to 8%, okay? So 6 to 8% within the 1 sigma range, plus and minus both counted. And if you look at 2 sigma range, this is negative 2 sigma, 2 sigma. What's the percentage of data that lies within 2 sigma range? That's about 95%. Okay, percent. If you look at the 3 sigma, the percentage of data lies within 3 sigma is about 99.7%. So what it means if your Ri is greater than 3, that basically means you are somewhere here. You are somewhere here. If the data you calculate falls in here, you can reject it. This is by using the rules we developed from the Z distribution. But right now we don't have Z because we are using estimated sigma. But the idea, the rationale come from here, okay? So basically, if you calculate the data that falls outside of 3 sigma, you can reject it. All right? So far, so good. We can use Ri to do some things. So immediately reject some data because you consider it's outlier. But what is the limitation of using Ri to identify outliers? What is the limitation of using Ri to identify outlier? So let's imagine in this case here, you have some data like this. And all of a sudden you have data somewhere here. If you don't have this data, just use the previous data, you would have a regression line like this, right? But if you do include this data alone will drag the line somewhere here. Because it's far outside, it's down below, right? It will drag this line too close to it. The least square principle will minimize loss. It's a summation of all loss. This data point have too much weight in the sum. It will drag it down to here. So if you just look at, depending on how severe it is, sometimes it has the effect of basically make the yi minus, what is the definition for yi? Make the difference here small enough so you don't even detect it, because this is for each I, right? If it drags the regression line toward itself too much, then actually yi minus y hat is not that significant. At the same time, when you look at all the other points here, because it dragged to itself, for other point, y minus y hat actually becomes large. So in that case, you may not be able to detect this point. Why? Because this one is called influential. It is an influential outlier. So the method we use here can detect the outlier right here. Let's say right here you have outlier. Regression line you estimated by including this point will still be like this. In that case, this one has significantly more EI than all the other data points. You can detect it, okay? So for this one, you can easily detect it. But for this one, because it will change the regression line, you may not be able to detect it. It can also, depending on how severe, it can also drag the line to here. So for this one, this is also an outlier, but by using Ri, you will not be able to detect it. So compare the two outliers. This is outlier, certainly because it's way away from the regression line. But this one is a non-influential outlier. You can detect it. This is an influential outlier. Influential outlier. You will not be able to detect it. So how do you address this problem? The idea here is in order to detect this outlier, I will use the regression function that is fitted by using data excluding this point. I use all the other data to fit a line. I get this equation. And then in that case, if this one has significant EI, it will be outlier. The idea is by deleting a point, in order to check if the ith data point is outlier, you would not use this data point in regression, okay? So this is called deleted residue. In order to distinguish from the new definition, we will call the original Ri defined like this. This one will be called internally standardized residue. internally standardized residue. So the new one will be externally standardized, okay? So internally basically means so far we have included the ice data point in order to detect the ice data point if it is an outlier. So if we delete this point when we do regression, it will be called externally. So we first define di equal to the difference between yi and yi hat, but with I like this. This basically means the regression line is using data excluding the ice data point. You get the regression function by excluding the ice data point. Then you use the regression function to predict xi. In other words, you would use the data point from 1 to I minus 1, then I plus 1 to n to fit this data by using your model. You calculate your beta, all the slopes. Then use that function to predict what if xi, what if the data is equal to xi. Then you compute what is the predicted value for xi. Okay, so this one basically coming from a different model. The model is created by using I minus 1 data point. Is that clear? All right. So this is called deleted residue. Then we standardize it. We call that Ri with the star. It will be di divided by. If we know the true variance, we would use the true variance. But here, let's just use the standard error of di. Okay. In the previous case here, at the bottom, this part, I didn't label that, but you should know this is the standard error of EI at the bottom, that's equal to sigma hat square root of 1 minus HII, okay? We plug in here, but we didn't tell you it's a standard error EI. Okay, so DI divided by the standard error of DI. How do you compute the standard DI? Well, this part to prove is very difficult. I will give you the conclusion, the result. You certainly are not required to do that, okay? So first of all, there's a relationship we can use. DI actually equal to EI over 1 minus HII. The proof at this point is beyond the scope of the class. We will just use this as a conclusion. It actually coming from the literature. A paper published in 1978 give you the relationship between the beta you computed by using the full data set and the beta with I, that one that you computed by using n-1 data point. From there, we can derive this relation. But right here, we will just use this as a conclusion. Okay, then the standard error of DI here will just be we call that MICE with I here. That include the MIC, you know, the SIC divided by its own degree freedom. But here, the SIC is computed by the ice point deleted. That's why you have I. Okay, this divided by 1 minus HII. That's the standard error. Standard error of DI. Putting this two together, DI divided by standard error of DI. Put these two together. This will be just what? EI divided by 1 minus HII. Then you divide by something, also have 1 minus HI under square root, right? So it will be just, let's see, EI over 1 minus HII. Copy from here, that's DI. divided by standard error of di, you have square root 1 minus hii over mise with ith point deleted. Okay. Right, one more step here. This can cancel one. You have square root of 1 minus hii. So you have ei over, so mise I here. Okay, mise with sub I here equal to sis with sub I here divided by the degree freedom. What is degree freedom now? Without this, it will be n minus p minus 1. But right now, you don't have n data point. You have n minus 1 data point. So that's why you have n minus p minus 2. Okay? So plug in what is mise ei in here. So you have ei over sse sub I n minus p minus 2, 1 minus hii. Okay, square root. You have to put everything under square root. That's all.